So lesson 4.8 here involves rate times time equals distance problems. Rate times time equals distance problems. You use that all the time. You might not realize it, or at least your parents do. If I travel 60 miles per hour for 2 hours, how far will I get? Anybody know? 120 miles, because rate of travel 60 multiplied by the amount of hours I spend at that rate will give me the distance of 120 miles with that little example I gave you. Unfortunately, the problems I give you at this stage of the game are not going to be quite so easy. You will need to take very, very careful notes and pay close attention. There are 3 different types of movement scenarios that we're going to talk about today. Okay? The first one is motion in opposite direction. This is example 1. Okay? Example 1 has you doing motion in opposite direction. So it could be a scenario where you leave your house and your friend leaves his house and you meet at a certain location, right? That's opposite direction. Another scenario might be you both start at a certain location and head home or wherever, okay? But in any case, it's opposite direction. Okay, the 2 things being compared are traveling in the opposite direction of one another. Okay? Bicyclists, Brent and Jane, start at noon from points 60 kilometers apart and rode towards each other, meeting at 1:30. Brent's speed was 4 kilometers per hour greater than Jane's speed. Find their speeds. Okay, based on the sketch, are they traveling towards each other or away from each other? Towards each other. I draw these sketches all the time. You don't have to, but for me it helps. So I am going to draw the sketches. They're traveling towards each other. Okay, it doesn't have to be accurate or anything. So maybe we've got Brent. Was the other one Jane? Now, how far apart were they? Did anybody get that from the story? 60 kilometers. So Brent's starting point was 60 kilometers from Jane's starting point. And that's exactly right. Okay? Now, we've got a distance of some sort. We have a rate, or do we? What do we know about their rates of travel? How fast they were biking? Comparing one to the other, maybe. If you look at the story problem, do we know anything? Brent was 4 kph greater than Jane. So Jane's rate was just rate, and Brent's rate was rate plus 4. Okay? Does that make sense so far, what I've added to this little sketch? Okay. Now, I'm going to take this, and I'm going to start a chart as well and just finish this off. We've got rate being multiplied by the time they spend, which will give us a total distance, right? We've got Brent, and we've got Jane. Now, you've already told me some information about the rates. Jane is just R, and Brent is R plus 4, right? Time. What do we know about the time? Go ahead. Very good. Both of them began at noon, and they met somewhere at 1:30. Noon to 1:30 is indeed 1.5 hours. Right? Now, in order to find distance, you have to multiply rate times time, yes? So that would mean up here in my little sketch, both of those pieces get multiplied by 1.5. Okay? So in my chart, that translates to 1.5 R plus 4 for how much Brent traveled, and 1.5 R for how much Jane traveled. What does that have to do with the 60 kilometers worth of distance? Any ideas? Say again? Absolutely. Clayton, good job. Yes. So whatever Brent traveled plus whatever Jane traveled covered the 60 kilometers that they were said to have been apart from one another. Therefore, Brent's distance added to Jane's distance has to equal the 60 kilometers that they were apart. Okay? Now that we've got this, all we've got to do is solve it. Brent added to Jane covered 60 kilometers worth of distance. Okay? And from here, it's just solving. We end up with 1.5 R. What's 1.5 times 4? 6. And that's the distributed version of this. Now, down here, all we've got to do is multiply that. And we end up with another 1.5 R. Added together, we get 60. Next step is to collect like terms, right? Now it's starting to look easy. 3R plus 6 equals 60. Are we able to solve it from here? I think so. Subtract 6. 3R equals, what do we end up with, 56? 54. Let's try adding, Mrs. Myers. Very good. Subtracting properly. Divide by 3, and you end up with R equaling 18. What does that tell us? Whose rate is 18? Jane indeed is 18. If Jane is 18, Brent is 4 greater. Makes him what, 22? If I can add. Therefore, B is 22 kph, and Jane is 18 kph. Okay? Motion in opposite direction. Turn the page. We're going to handle motion in the same direction now. And this type of comparison is often used when comparing travel abilities. Are you going to take a car or a train? Racing. Is car A going to beat car B on the drag strip? Things like that. So a good sketch would be, so let's just say, like I said, I'm certainly not a artist. Wow. There's my helicopter. Maybe I should put, I don't know. There's my helicopter. Helicopter is going in that direction versus airplane. Okay, helicopter and airplane. Airplane's a little less weird. Now, they're both heading in the same direction. Let's see what happens. A helicopter leaves Central Airport and flies north at 180 miles per hour. 20 minutes later, a plane leaves the airport and follows the helicopter at 330 miles per hour. How long does it take for the plane, now the helicopter's ahead, how long does it take for the plane to overtake the helicopter? Okay, let's see what we know. We know, and I'm not going to write too much here, but we know, again, rate times time equals distance, right? We know the helicopter has some information. We know the plane has some information. Did they give us clear-cut rates? Helicopter's 180. The plane is 330. What do we know about time? Any ideas? The helicopter leaves Central Airport, flies north 20 minutes later. 20 minutes later. So you can translate that any way you want. You can call the plane T, and you could call the helicopter T plus a third of an hour. Why? Because 20 minutes translates to a third of an hour, and they gave us our rate in terms of miles per hour. Okay? So when they tell you minutes, you have to make sure that your rates translate the same way. Okay? I couldn't put 20, because it's not 20 hours, it's 20 minutes, which is a third of an hour. Okay? So the distance the helicopter traveled is 180 t plus a third. Rate times time equals distance. The distance the plane traveled is 330 times t. But how far is the distance? Remember our last scenario, Jane and Brent added together equaled whatever it was, 60? But we don't have that this time. We want to know when will, they both started at the same place, helicopters flying along, when will the plane overtake them? At that point, the mileage would be equal, wouldn't it? Because if the helicopter and the plane start from the same location, and the helicopter's just puttering along, okay, and the plane, at this point, the plane has overtaken the helicopter. In other words, caught up to. At that point, their distances are equal to one another. That means that the scenario 180 t plus a third equals 330 t. And by solving for t, you find out how long it takes in terms of hours for the plane to catch the helicopter. Okay? When the helicopter overtakes, or when the plane overtakes the helicopter, their distances are equal. So you can equate this with this. Solving from here, 180 t plus 60, because 60 is 1/3 of 180. All of that equals 330 t. Let's collect our t's on the one side there by subtracting. And you end up with 60 being equal to whatever the difference is, 150 t, if I did my arithmetic correctly. Divide by 150. And t equals whatever the reduced version of that looks like 2/5. 2/5, what the heck is that? 2/5 of what? What are we talking about? Minutes, hours, years? Hours. The entire thing has been in terms of hours. Miles per hour. 1/3 of it, or 20 minutes later, which you translated to hours. So 2/5 of an hour is, let's see, 12, 24 minutes? if I did my arithmetic correctly, 2/5 of an hour is 24 minutes. Okay, that's how long it takes for that plane to zoom up to and then pass the slow helicopter. Okay, so we've done opposite direction. They're either coming at each other or going away from each other. We've done same direction, in which case this scenario had the distances of one catching up to the other, which meant their distances became equal at a certain point. The last one is round trip. Okay? And this is also useful for travel. Maybe going somewhere is uphill and then returning is downhill. If you're traveling in the mountains, that plays a part. Racing in the mountains, that plays a part. Skiing, it definitely plays a part, because in order to get to the top of a ski slope, you've got to putter on a ski lift for like an hour. And then you get to the top and it takes you like 20 minutes to come down. Lots of fun though. So, I'm not going to draw a skier, but I do know that round trip would imply something like this. Okay? And the question they have for us is Maria going up on the pokey lift and skiing down at an awesome fast clip. Any of you ever skied in the mountains before? Oh, Lake Tahoe was great. So, what do they tell us? A ski lift carried Maria up a slope at a rate of 6 kph, and she skied back down right underneath the lift, parallel to. Okay, that way we know that it's the same distance. Up, down, like going upstairs or downstairs. Okay, she skied underneath the lift at 34 kph. The round trip took 30 minutes, which is a half hour. Would you agree? So there and back was 30 minutes. How far did she ski and for how long? Okay, so I've got up and I've got down. Okay, and I know that the two trips put together was a half hour. So I am going to say that the time she spent going downhill, I'm just going to call it T, and since the total time spent is a half hour, 1/2 minus T has to then be only the uphill battle. Okay? Because if you have a total and you remove a part, you get the other part. Okay? We have a total and we remove a part, we get the other part. Okay? In chart form, I'm going to call it up and I'm going to call it down. And I'm going to say rate multiplied by time equals distance. Uphill was 6 kph, downhill was 34 kph. The rate I assigned for uphill is a half hour minus the downhill. The downhill is just the downhill. Therefore, this becomes 6.5 minus t, and the downhill becomes 34t. Now, uphill, downhill. What do we know about the distances? Did they actually give us a mileage or a kilometerage for that matter? They're equal to one another. Very good. They're absolutely equal. Just like this scenario where the plane and the helicopter end up catching up to each other, out and back is the same thing, which means these two items equal one another. 6 times a half hour minus the downhill has to be equal to 34 times the downhill time spent. Okay, the uphill distance equals the downhill distance. All right, 6 times a half is 3. 6 times t is 6t. 34t. Add 6, you end up with 3 equaling, is it 40t, if I'm doing my arithmetic correctly? Divide by 40. And t equals 3/40ths. T equals 3/40ths. So in order to figure out what 3/40ths is, in decimal form, we know that the time spent going downhill, is 3/40ths of an hour. I would rather convert it to a decimal, which they did, which was 75 thousandths of an hour. Multiply that by 34, which is his rates. Now we know his rates. Multiplied it by the actual time that he spent downhilling. You could have done it up here too, but I just think this is easier. And you end up with the distance traveled from top to bottom. 2.55 kilometers. And that, my friends, is how far she skied. This is how long it took her to ski.